All right. Before we go on and practice some more with vectors and then continue on to describe velocity and acceleration in terms of vectors, I want to go back and mention just one bit of notation that I think I glossed over and didn't give enough time to on this slide, where we were talking about the three different ways to specify a vector. One is to give the length of the vector. Length is the same as the magnitude of the vector. So magnitude and length are used interchangeably. That's how long the vector is, and it has some units associated with it. If it's a displacement vector, the units might be meters. The notation for that is if you have a vector whose symbol is d with a little arrow over the top of it, right, as is appropriate for a vector, the length of the vector is a scalar, and by convention we usually write it, the length of the vector, as just the symbol we use for the vector without the little vector symbol over the top of it. So if we have a vector f with an arrow over it, the length of f will just be denoted by the plain letter f. That's shown right here. Occasionally, we will, that notation doesn't work so well because of the way the vector happens to be defined, and we'll see that coming up. So an alternative way to represent the magnitude or length of the vector is just to put the vector in the middle of absolute value signs. So when we have a vector symbol and we put it inside absolute value signs, that also is another way to denote the length of the vector. And sometimes you use one, sometimes you use the other. We just have to get used to both of them. All right, continuing on, we talked a little bit about components and different ways to represent a vector. Now we're going to talk about one other bit of mathematics that we need before we go on and get back to the physics and use this in the context of physics. And that is how to do operations with vectors. We need to know how to add, subtract, and scalar multiply vectors or rescale vectors, and how to denote those. So let's start with addition, then we'll go on to subtraction, and I think in the next video, scalar multiplication. Let's imagine we have two vectors, r and s, and we're going to denote the components of r and s as usual, xy components, as rx and ry and sx and sy. We're going to define a new vector, which is called r plus s. Okay, r plus s. I could say the vector r plus s is some new symbol b vector, but r plus s is a perfectly legitimate notation for a vector. So we think of when you add two vectors, you get another vector. It's a new vector, and this is the notation we're going to use for it. And how do we get the components for the new vector, the xy components? Well, we do kind of the only thing that possibly makes sense. To get the components of the vector denoted by r plus s, we take the sum of the x components, and that gives us the new x component of the new vector, and this add together the y components, and that gives us the y component of the new vector. We'll talk about why we would ever want to do this in the future, but for right now, just think of it as a definition. That's, by definition, how we add vectors if we know their components to get the component of the sum. What about if we're representing our vectors by arrows? For example, I've drawn two kind of random vectors here. Here's a vector r and here's a vector s. I'm not worrying about the components, I'm just representing them as arrows. How now can I get a picture of what the vector r plus s looks like? I don't really care where the tail is. Remember, we can always move vectors around as long as we don't change the magnitude or direction. But I want to be able to construct the vector out of these two vectors. So here's how we're going to do it. We'll have two different methods, and I think the book goes through both of these. One is called the head-to-tail addition method. And again, relying on the fact that it doesn't matter where we draw these vectors. I've just taken r and redrawn it over here. And then I've taken s and redrawn it so that the tail of s is at the same place as the tip of r. Notice the arrowhead of r is there. I placed the tail of s there. And that's why it's called the head-to-tail addition method. I take the head of one and place it at the tail of the other. And then to get a picture of what the vector r plus s is, what we do is start from the original tail and go to the final tip and draw a vector going from the original tail to the final tip, that will be a picture of the vector r plus s. And if you start thinking, draw these in some xy axes and draw out what the components are, you'll see that this vector is completely consistent with this definition we gave up here. They're really doing the same thing, although it feels a little bit different. So that's how we add pictures, arrow pictures of vectors using the head to tail method. Here's an equivalent method that I think is also covered in the book. It's called the parallelogram addition method. If you take your two vectors and move them so that their tails are at the same location. So I draw R and then I place the tail of S so that it meets the tail of R. Once I've done that, what I'm going to do is turn the pair of vectors into a parallelogram by drawing in a side that's parallel to S and a side that's parallel to R so that we form a parallelogram out of R and S. And we start from the original point where the tails were joined and we go to the opposite corner, and that will give us a picture of R plus S. Why do we have two different methods for doing it? Well, sometimes you'll just happen to have your vectors drawn so that the tails meet, and you'll want to use the parallelogram method because it's the path of least resistance. Sometimes it's easier to add them tip to tail just because of how you see things in a diagram or something like that. So it's useful to know both of them. Now, why would we ever make such an abstract definition of how to add vectors? Well, here's one example. We said we are going to represent forces by vectors, right? A vector force represents how hard and in what direction I'm pushing on something, or a certain object is pushing on it. Now, we might have an object where more than one thing is pushing on it, and we might want to ask ourselves, what is the overall force that is being exerted by both of those? And the overall force, which is going to determine what the acceleration of that object is going to be represented by the sum of those two vectors. So when we want to find out the overall force, I might say, I've got some electric charges sitting around the room, and I've got another electric charge that I'm concerned about here, and I want to find the total electric force on it. Well, I could find the electric force from the other two charges and figure out what they are, and what I want to do is add those two to get the overall electric force on the charge. So in any case, it's going to come into adding forces among other places. So that's one reason why the definition is important. Okay, a little voting question. Which of the vectors best represents the vector sum of p plus q? So here's a vector p drawn here and a vector q drawn there. If we want to visualize the sum of those two vectors, which is the only one that's reasonably close to it? Okay, the answer is selection A, and I can see that by the fact that these two vectors are set up with their tails at the same location, so that makes it very convenient for me to visualize the parallelogram method. So to do the parallelogram method, I form these into the only parallelogram I can make with it by drawing a side that's parallel to P and a side that's parallel to Q, and that opposite corner would be over here where I'm pointing to right now. So I start from the point where the tails are joined and go to that opposite corner. It's a vector that roughly looks like that. That looks close to what A is there. So A is the correct answer through the parallelogram method. To use the tip to tail method, you have to do some mental gymnastics and move those around in your mind. So that's not the best method here. All right, second operation is subtraction. Again, just changed a few things in the same slide. If you know the x and y components of vectors r and s, we're going to define a new symbol for a new vector. Here's a new vector that we're going to call r minus s. And of course, its vector components are rx minus sx is the x component of this, and ry minus sy is the y component. Notice in this case it matters which order you take them, right? R minus s is different than s minus r, would have different components. That's how you do it with components. Now, how do we do it with arrows? So again, here are my randomly chosen r and s vectors. How would I draw a picture of r minus s? Well, one way to do it is based on the tip to tail method. What we're going to do is define the vector minus s. You know, just like when you say, I want to compute 7 minus 3. Well, that's the same thing as 7 plus negative 3. We're going to do the same kind of trick here. The vector minus s is a vector that has the same length but goes in the opposite direction from s. Right? So if I want to draw a picture of minus s, and we'll make more sense out of this when we talk about scalar multiplication. But if this is a picture of s, this is a picture of minus s. So what I've done is taken the vector r, redrawn it over here, and drawn the vector minus s with its tail to r's tip. So it's the tip to tail method. And so then I think of r minus s is the same thing as r plus negative s. And I just use the tip to tail method. I start at the original tail and go to the final tip. And so this is a picture of r minus s. That's one way to construct it. And if you think about the components, you could convince yourself, I'm not going to make the argument now, that this way of adding them is completely consistent with the diagram we've drawn down here. Another way of doing it is it's sort of similar to the parallelogram method. What if I have my vectors so that their tails are at the same location as I've drawn them in this diagram right here? How do I then visualize r minus s? What we do is start at the second one, the tip of the one that's being subtracted, and go from that tip to the other tip, right? So we always end on I go from tip to tip in that diagram, and I end on the one that doesn't have the minus sign on it. So I start at s and go to r. That's a different way to subtract arrows. Why do we care about this definition? Well, we are going to, when we calculate the displacement of an object. So for example, I tried to make a little symbol that looks like an ant here. Here's an ant walking around the xy plane at time t0 relative to the origin. It was at position r0. So there, relative to the origin, that's where it was at time t0. At time t1, it was at position r1 relative to the origin. So maybe it went from here, it went on some circuitous path, and it passed that point down there. What's its displacement? We already said the displacement we're going to draw just from the initial location to the final location. Well, notice that these two vectors relative to the origin, where it was at time t0 and at time t1, have their tails at the same location at the origin. And therefore the difference, the displacement vector, which is just going to be the final minus the initial, just like when we do, delta t is the same thing as t final minus t initial. Delta r is r in the final time minus r at the initial time. And when we subtract two vectors where their tails are located at the same location, we just draw a vector that goes from one tip to the other tip if the vectors happen to be drawn with their tails co-located. And when we do that, we always, whichever one is the first one in the subtraction, we end on that vector. And that's consistent with what we know about displacement, right? In displacement, we should always go from initial to final. And when you subtract two vectors, we always write them as final minus initial. So the first one to come in there is final. We should end on that one. Okay, so we're going to want to do things like displacement. We'll also want to find differences of other vectors, and that's one reason we would want to have this definition, even though it seems natural from the components especially. That's why we would care to make that definition. All right, same vectors p and q we had before. Now what about the vector difference p minus q? Which of these is the best, most likely correct answer for a picture of p minus q? Okay, the answer is selection B, and that is because the vectors have their tails at the same location, we know the difference between the two vectors starts at one tip and ends at the other tip. The only question is, should it go this way or this way? And the idea is you always look at the one that appears first in the subtraction, and that's where you end your arrowhead right there. So we should start here and end on the first one in the subtraction, the one without the minus sign. So the best answer is B. Sometimes people, for some reason, select D, and I'm sympathetic, D's not that far off, but it would sort of end up over there. It wouldn't be really close to it. So the only reasonable answer here is B. Okay, let's finish up by starting a worksheet problem. So check the website for adjacent to this video, this next worksheet problem. And here we've got two vectors, A and B, and I want you, given their magnitude and direction on the paper, what I want you to do is draw a vector which looks like A plus B. It's got the right magnitude and right direction, and one that's A minus B. Same thing for the two vectors that are given in problem 2. And when we come back, we'll look at the solution to that and continue on.